Hey everyone, this is the outline for today's class. First, we're going to study what is thermodynamics. Within this topic, we're going to see things such as historical perspective about thermodynamics, classical thermodynamics and what it exactly means, and zero law of thermodynamics. Next, we're going to move to definition of some terms that are important to understand thermodynamics. As those terms, we can say things like system and universe, and then types of systems. Finally, the last topic of this video is things like thermodynamic changes that may happen in the ideal gases. So, historical perspective about thermodynamics. The very first machine created using concepts involving thermodynamics was the first vacuum pump ever, what was created by the German scientist Otto von Guericke in 1654. Then, during the next 2 centuries, and due to intellectual and industrial revolution, we have seen the advent of many things related to thermodynamics and many laws and ideas. Among those, we can remark the discoveries made by Robert Boyle. He was a British scientist who derived the law that governed the behavior of pressure and volume in gases. This development was made in 1660. Then, after him, another remarkable scientist is Gay-Lussac. This French scientist built up his work about 1802, and most of his work was related to the previous discoveries made by a scientist called Charles, a British scientist. And Gay-Lussac collected Charles and his own findings and formalized everything. In such a way, he had a very good portray about all the laws governing pressure variation according to temperature in gases. After that, we have like scientists that contribute to a formal development of thermodynamics. Before that time, thermodynamics was very empirical, and although it has been useful to explain many things, it has not been for the others. Things were difficult to generalize, were difficult to find common ground. And then Sadi Carnot was responsible to formalize many of the previous ideas in his book called Reflections on the Motive Power of Fire and Machines Fitted to Develop That Power. This book was written by Carnot in 1824, and it underlines all the bases for the second law of thermodynamics. It formalizes the things for the very first time and also introduces concepts like thermodynamic efficiency and the idea that heat is transferred from the hotter body to the colder body. So, what is thermodynamics? We have talked a lot about historical perspective so far, but for some of you, we are not completely familiar what thermodynamics exactly mean. The very first resource to look for probably would be a dictionary, and according to Oxford Dictionary, thermodynamics is the branch of physical science that deals with the relations between heat and other forms of energy, such as mechanical, electrical, or chemical energy, and by extension of the relationship between all forms of energy. This seems to be a very formal definition. For some people, it may not be very immediate what it should be. So if we could summarize in fewer words what thermodynamics is, we could say that thermodynamics is the study about how energy is transferred between different forms and systems. And why is it important to study thermodynamics? Probably never noticed or never realized, but thermodynamics is very present in our everyday lives. For instance, whenever you go to a grocery store, all packaged products that you see in that grocery store, they have a nutrition facts label. And on the top of that nutrition facts label, one of the very first piece of information that you can find is the amount, how many calories that food can provide per serving. Okay, and calorie is an energy unit, is a unit that's related to energy. Although it's not a standard unit, international system unit, it's a unit very commonly used. Okay, and basically it's very thermodynamically related because that information says to you how much energy your body can uptake from that certain food per a portion of that certain food per serving. Okay, another moment that thermodynamic is really present in our lives. For instance, in cars. Everybody here has seen like probably a car engine, and you have seen that sometimes the power that is able to be delivered by a car engine is given in horsepower. Okay, so horsepower is a unit of power, and it's completely related with that mindset, with all that idea present during the Industrial Revolution, okay, where actual vehicles did not exist yet. Okay, and it's one more unit, it's one more area where thermodynamic is present. Okay, so being more specific, we can say that thermodynamic is really broad. Many things has built up during since the 17th century until now, and many things are still in development, but the branch of thermodynamics that is important for college level and the branch that we're going to focus on is the classical thermodynamics. So what is classical thermodynamics? Uh, Classical thermodynamics is the branch of thermodynamics that studies phenomena that happen under equilibrium condition. Okay, so probably you are familiar about equilibrium, might be in some situation, but not chemically yet. So first, let's see a common life example of what equilibrium is. Okay, so for instance, we have two kids with, let's consider, equal mass, so they weigh the same, both kids, and they're playing in a teeter-totter. Okay, and the pivot point of the teeter-totter is located right in the midpoint or the center of mass of the slab where the kids are sit on their edges. Okay, so in this case, as the pivot point is located in the exactly the center of mass of the slab, and the kids, they have equal mass, so the teeter-totter does not move higher level to one side and lower level to the other side. Instead, both edges of the slab, they remain the same level, which could be considered as an equilibrium situation in this case. Okay, then this equilibrium can be disrupted by either by moving the pivot point away the center of mass of the slab, or in another case, putting the kids with like masses that are reasonably different between them. So in this case, the teeter-totter, the heavier kid would be in a lower level, lighter kid would be in a higher level, and that would be an example of a situation that was taken away from a previous equilibrium. Okay, so this is it's not a chemical equilibrium in this case, it's something more mechanical, but it is necessary to introduce that idea about equilibrium on people's mind. Okay, now let's think about chemistry. So chemically speaking, equilibrium in a chemical reaction setting would be that moment when the concentration of the reagents and the products, they don't change. Or another definition would be we have a forward and a reverse reaction. So in equilibrium, the rate of the forward and the back reaction and the reverse reaction, sorry, they become the same. They become the same rate, okay? And for that reason, the concentrations of the reagents and products, they don't change anymore, okay? And we have seen that most of the situations, the thermodynamic can be very broad, and many phenomena, they don't happen in the equilibrium. But equilibrium is still important because equilibrium can be used to at least give a rough idea about how much product would be formed in a certain reaction, how much reagent will be consumed, okay? For instance, the maximum amount of product possible to be formed in a reaction is that amount of product that's formed during the equilibrium, okay? So you can use that at least as a first starting point to have an idea about how large or how good or bad will be the yield of a certain reaction, for instance, okay? Then the thermodynamic is rooted completely in a base that's called Zero Law of Thermodynamics, and it was formalized by Sadi Carnot in his book from 1824 that you see a couple of minutes ago, okay? And the zero law of thermodynamics involves that concept of thermal equilibrium, okay? Not chemical equilibrium exactly, but more thermal equilibrium in this case. So suppose that you have two bodies that they have very different temperature between them, and then they are in close contact, okay? So we have the left side a higher temperature body and the right side a lower temperature body. Then when they are in contact, the heat is going to be transferred from the body in higher temperature to the body in lower temperature. That's how the heat is going to flow, okay? Always from higher temperature to lower temperature. That's the zero law of thermodynamics. Then there is a limit where that heat will be transferred from the hot to the cold body. And that limit will be set by the when the thermal equilibrium is reached, okay? So thermal equilibrium is reached when both bodies they are exactly at the same temperature. Now we don't have anymore a cold and a hot body, but we have two bodies in intimate contact, both at the same temperature. That moment we can consider that equilibrium was reached, okay? And that is the definition of the zero law of thermodynamics again. Heat is transferred from the hot body to the cold body until the thermal equilibrium is reached. In other words, until both bodies have the same temperature. Now, it's necessary to define some terms before starting a more in-depth study about thermodynamics. And those definitions, the very first term to be defined is what is system? Okay, a system is that portion where the thermodynamic changes are happening, okay, where all the heat transfer has happened, okay. So in the previous example we have cold and hot body in contact, and energy was transferred from the hot to the cold body. On that example, a system would be the hot and cold body in intimate contact, okay. That would be an example of the system. The context of a chemical reaction in solution, it can be your beaker, it can be, for instance, in the combustion engine, it could be the engine itself, and all those things. In summary, a system is the place where all the thermodynamic change of states are effectively happening. Okay? Then we have the concept of surroundings. Okay? It's really important. Surroundings are all that region that are immediately close to the system, and surroundings they can have a very important role in the final thermodynamic in the change of thermodynamic state from the system. Okay, the system can interact somehow with the surroundings. Okay, and then system plus surrounding, they form what's called universe. Okay, so a universe is a junction of system plus surrounding. A thermodynamic universe is system when uh, all thermodynamic changes are happening and its respective surroundings, where are the immediate region close to the system and can be somehow involved or influencing the thermodynamic changes happening in the system. Those things they form the universe. So we have seen that a thermodynamic uh, system, there's the system and surrounding, they two together form the universe. And now we're going to see that there are different types of systems. And the systems they're defined according to the type of boundary and that separates the system from the surroundings. Okay, and in other words, a system is defined about according to how its boundary with the surrounding behaves in relation to the exchange of energy and matter between the system and surroundings. Okay, based on that definition, there are three types of systems. They are called open system, closed system, and isolated system. We're gonna see each of them more in depth from next slide, okay? So first, let's see what an open system is. Op let's see, we have the system and surrounding as we know, as we have just studied, okay? Then let's imagine that there's like a boundary that physically separate the system from the surroundings. And that boundary allows energy to be exchanged between system and surrounding. But not only energy, matter can also be exchanged between system and surroundings. So based on this definition, we can say that open system is a system where energy and matter can be exchanged between the system and surroundings. Next, what is a closed system? So we have system and surrounding again, but just energy can be exchanged between system and surrounding. No matter can be exchanged in the case of a closed system. Okay, so closed system, only energy can be exchanged between system and surrounding, but no matter. Matter cannot be exchanged. And third, isolated system. So we have system and surrounding, and in this case, no energy and no matter can be exchanged between the system and surrounding. Okay, the system is completely isolated, as the name says, from the surroundings. So isolated system, we can formalize and say that neither energy nor matter can be exchanged between system and surroundings. Now we're gonna pass through the study of thermodynamic changes, okay? And a very common system while studying thermodynamics is a cylinder having a piston on its top, and the cylinder is completely filled what it's called ideal gas. Okay, so we have the cylinder, and then we have a piston on its top, and the piston can move upward and downward completely uh, weightless and frictionless, okay, very freely without any loss of energy due to the friction or the motion of the piston, okay, and piston is considered to having no mass at all, okay. So yeah, we have a cylinder, piston, which can moves downwards and upwards, okay, and it can take to thermodynamic change in the system, okay. And then, as told before, the cylinder is completely filled with ideal gas, okay. So what is an ideal gas, okay? Ideal gas, it would deserve a completely separate video for that, and you are going to have a video for that. But we can say that ideal gas, if you mathematically speaking, and a short notes definition, ideal gas is a gas that obeys the ideal gas law, which is given by the following formula: P times pressure times molar volume equals to gas constant, which stands for R, and temperature, okay? That's how it's defined. And P would be the gas pressure, V subscript M would be the molar volume. The molar volume could be defined as the effective volume divided by the number of moles of gas, of the ideal gas. Then R is the gas constant, and T is the temperature, okay. So ideal gas, they obey the ideal gas law, okay. But it would deserve a more formal definition. For instance, does any gas can be an ideal gas? Or, I mean, what is necessary to be very close to the ideal condition to take a regular gas and put that regular gas in a condition where it would be able to behave as an ideal gas, okay? And ideal gas, basically what characterizes ideal gas is the fact that we can consider that the interactions between the individual gas molecules are so negligible that we can consider that practically there is no interaction between individual gas molecules, okay? That's the main feature necessary for a gas to be considered ideal, okay. And we can reach that ideality condition by varying pressure and temperature. For instance, if you are in a very low pressure, so you can understand like the gas molecules will be very dilute, okay. We are gonna have very low amount of molecules for a relatively large volume, in such a way the pressure becomes too low, and the molecules, they get very apart from each other and they don't interact anymore, okay, because they're very so apart from each other. So low pressure would be one condition where there's no interaction between the individual gas molecules. The other condition will be high temperature. So high temperature, they move like very fast and such a way that there's less chance to them to interact with each other, which takes to ideality again, okay. So ideal gases, they're like practical reasons they are not that common to the regular conditions that you use gas, but they are like they're a good system model to study the very concepts in the thermodynamics, okay, to introduce thermodynamics, okay. And let's see, the ideal gas equation is a state equation of the state, okay. So which means that for a set of variables, pressure, temperature, molar volume, okay, if we know any two of those three conditions, the third condition is known as well, okay? The value of the third condition is completely linked to the value to the other two known conditions. For instance, if we know the pressure and temperature, consequently, due to the property of the ideal gas law being an equation of the state, we know the molar volume as well. Next, the same way, if we know the pressure and molar volume, we know the temperature that ideal gas system might be. And finally, if we know the molar volume and the temperature, we know also the pressure where that ideal gas system might be subject to, okay? And as a state, we can understand as a state like any set of pressure, molar volume, temperature condition that a gas can be subject to, okay? And one ideal gas system can change from one state to another state, okay? And there are four types of changes that are very commonly possible, okay? So the isothermic changes. Isothermic changes are those changes of states where the temperature is fixed, so the temperature does not change between the initial and the final state, but the pressure and the molar volume, they change, okay? So this is what called isothermic change. Isobaric change. Isobaric change are those that pressure is fixed between the initial and the final state. Pressure does not change, but volume and temperature, they really change. Next, we have isovolumetric change. Isovolumetric change are those changes where the molar volume changes from the initial and the final state, but not pressure nor temperature. So pressure, temperature, they don't change. The same way, there are thermodynamic changes that nothing is kept constant, that pressure, molar volume, and the temperature, they can change in comparison to the initial condition, to the initial state, okay? So those are the types of thermodynamic changes that an ideal gas can experience. Now let's see an example of a possible application of ideal gas law. So we have the ideal gas law, and if we isolate the gas constant R on that formula, we end up having the following formula, that R is equal P times molar pressure times molar volume divided by temperature. And we can take advantage from the fact that R is a constant, and from that we can try to relate different states just by using this mathematical property to isolate R, and R is a constant, so being equal all the time, okay? So let's see one example, very close example about how we can do that, okay? So suppose you have a thermodynamic system constituted by the cylinder filled with ideal gas molecules with a piston in the top, and the initial state where that system is subject to is, we have the cylinder and the initial temperature is 350 Kelvin and the pressure is equal to 3 atm, okay? And the value that we're going to assume for the gas constant in this case is 8.2 times 10 to the minus 2 atm times liter over mole times Kelvin, okay? So if we plug the R, the gas constant R, temperature and pressure values and the ideal gas law, we should be able to obtain the molar volume occupied by those ideal gas molecules. And if plugging those values, we arrive to the fact that the molar volume is equal to 9.6 liters per mole. Okay, so we have defined the three variables related to this initial state. We have pressure, volume, and temperature. So a pressure of 3 atm and a volume equal to 350 Kelvin should relate to a molar volume of 9.6 liters per mole. So that's our initial state. And then let's suppose this system will be subject to isothermic change. Okay, so the temperature of the system will not change, but the pressure is going to decrease from 3 atm to 1.8 atm. Okay, then let's try to figure out what would be the molar volume of the final state. So we can, to figure that out, one way to solve that, we could plug the values in the ideal gas law from the final state, as we have the pressure and the temperature in that case, but it should work. But let's see a more general case where could be applied also for the case when nothing is kept constant. Okay, so we could use that formula by isolating R from the ideal gas law. Then we have pressure times molar volume over temperature, and as the gas constant R does not change, so pressure times volume, molar volume over temperature for the initial state will be equal to pressure times molar volume over temperature of the final state. This formula on the bottom is really important, and it could be used for any type of transformation or change in the idea of state in the ideal gas. Isothermic, isobaric, isovolumetric, and also for those that they don't, cases where nothing is kept constant. Okay, so let's plug the value for the initial and final state to this formula. Okay, so by plug them in formula, we come up with an answer equal to 16 liters per mole as the molar volume of the final state. Okay, so the final state has the following conditions: pressure 1.8 atm, temperature the same as the initial state, 350 Kelvin, and a molar volume of 16 liters per mole. So we can conclude from that, first, if in an isothermic change, if the temperature decreases, the molar volume should increase. That's exactly what we obtain. As a way to double check your answer, alternatively, you can solve just applying the ideal gas law to the final condition. So you can go to the ideal gas law and plug pressure equal to 1.8 atm, temperature equal 350 Kelvin, and if you're right, you should arrive exactly the same 16 liters per mole molar volume as we did here in this example. So I leave that to you to do as a way to double check and sharp your skills. Okay, thank you so much for your attention. That's the end of this class about introduction to classic thermodynamic and change in the states in the ideal gas. Thanks for your attention. I hope you like, and if you like it, like our video down there, Leave your comments that you think are relevant to the video, and please subscribe to our channel. See you later. I hope you enjoy. Bye.